Okay, now is the third video on neural engineering framework stuff. This time we're going to be talking about dynamics. So to recap, we talked about population coding. You can represent numbers or vectors of numbers into the collective activity of a population of neurons. And you can decode from that population values or even those values or nonlinear functions of those values by choosing the decoding weights. Now you can have a population that's encoding some vector, and it can project through to another population, and you can perform a transformation on this data that gets re-encoded into this population through the connection weights. It's basically just a matter of computing the decoders and using those decoders and the encoders to set up the connection weights between the two populations. So now we're going to take a population and make it recurrent, feed it back into itself, and we can decode from a population different functions of what's encoded in it to re-encode recurrently, and that can implement different dynamical systems. So the goal here is to see how to build dynamic recurrent networks using population coding methods. So consider a dynamic model of a leaky integrate and fire neuron that contains two time-dependent processes. So we talked about the formula or the differential equation that governs the membrane potential of an LIF neuron. But in addition to that differential equation, there was the input current had to be sort of collected, and so the input current also was a dynamic process. So it's these two differential equations that work together. So this first one, S, is the current. So let me label this first equation as current. So S is current, and the differential equation is basically take the input. So the current is constantly integrating the input, but there's also this leak term, or it's not really a leak. It's basically a decay term. But we'll talk about how the equilibrium solution, how that decay term and the input current go together. Then finally, here's our good friend, the time constant, or in this case, synaptic time constant. Synaptic time constant. Okay, now that's the input current, has that dynamic process. Now the membrane potential, V, also has a similar dynamic process. This is the membrane time constant. Now this also has a decay term and some function of the input current. Now, this is not this is kind of a more general model. In the past, I think we just had the membrane potential was just integrating the input current, but we can also have it run through some nonlinear function in addition. Let me move this over a bit here. So this is the activity of the neuron. So we got a differential equation for the input current and a differential equation for the actual activity of the neuron. So what we end up with is a population of neurons that we can call the activity is V1, but the input current is S1. And the next neuron is activity is V2, sorry, and the input current is S2, and so on. The input current, input to that neuron is C1, input to that one C2. So each neuron has a different input, gets turned into, or gets integrated by the S, the input current variable, and then that gets integrated into V, into the membrane potential or voltage. All right, so just quickly recall previous forms of sigma of S. There was a lift tuning curve that looked something like this. The logistic curve, which look like that. And then the hyperbolic tan function goes between +1 and -1 and passes through 0 along the way. So let's talk about the dynamics of this 2-equation neuron model. One way to understand the dynamics is to look at its equilibrium solutions. So remember, equilibrium for a differential equation, an equilibrium solution is the solution that you get when you set the derivatives to 0. Because if the derivatives are 0, that means nothing's changing. All the variables are constant and fixed. So if we look at the current equation, the input current equation, synaptic time constant times ds by dt equals -s plus c. If we suppose that input is constant, if that's constant, then we can talk about the steady state solution. 'Cause if the input keeps changing, then S is not going to stay in equilibrium. It's going to keep changing with the input. But if the input is constant, then we can expect S to go to some equilibrium solution. So at equilibrium, we set ds by dt equal to 0, which gives us 0 equals -s plus c. I'm just copying that equation up there, setting the derivative to 0. And then we can solve for s. Therefore, s equals c. So this is a situation where over time, you got some value. C is a constant input. S, whatever it is, this vertical axis is S. Oops. And then we got this value C. S will migrate towards C like that. And how quickly it migrates towards C depends on the time constant. What about the membrane potential, V? So its differential equation is tau sub m times dV by dt equals -V plus sigma of S. So suppose this is constant. Then we get, at equilibrium, dV by dt must be 0, which gives us V equals sigma of S. So this is kind of, no, that's what I'm going to say next. Okay. So great. We know what the equilibrium solution looks like for each of those two dynamic variables for constant input. Now let's say tau sub m is much smaller than tau sub s. So what does that mean? Remember, tau sub m is a membrane time constant, and a time constant is basically it gives you some time scale for how quickly things happen. With a small time constant, if tau is small, that means things are happening quickly. It's got a small time scale. If tau is big, that means things are happening slowly. Okay, so if tau sub m is much smaller than tau sub s, that means V is updating more quickly than S. V is more dynamic and faster changing than S. So if in this case, the neuron membranes react quickly, i.e. they reach equilibrium quickly compared to the synaptic dynamics. The V reaches equilibrium quickly compared to the synaptic dynamics. So in that case, it's a reasonable or quite a common approximation to assume then that V reaches equilibrium immediately, or basically compared to S, V will always be in equilibrium. So S is constant relative to V, because S is changing slowly. Tau sub S ds by dt equals -S plus c. So S and V are changing, but S changes much more quickly. Sorry, the opposite of that. S and V are both changing, but V changes very quickly. S changes very slowly. It's kind of like how we see the day and night, day and night, day and night. There's a very fast process. and the seasons changing as the Earth goes around the sun is a slow process. So according to the day and night fast environmental change, we think of the sort of where you are in the season as relatively constant as day turns to night and night turns to day. I don't know if that's a very helpful example, but in this case, when V changes quickly, it's basically at equilibrium compared to how slowly S changes. So because of that, we can pretend that S, compared to V, we can pretend that for the for the voltage equation, we can basically pretend S is at equilibrium because V is at equilibrium because S changes so slowly. We can think of S as constant relative to V. That's what I meant to say. I hope I made that relatively clear. I'll go through the same logic in the opposite. Let's suppose the synaptic time constant's small, so which means S goes to equilibrium really quickly and V slowly migrates. So compared to V, S goes to equilibrium really quickly. So we can really just represent S as its equilibrium value. But V takes time to get there. Actually, we can put really that if we want, but I won't. Let's just put S there. Okay, so in that case, the input current is at equilibrium, and the membrane potential, or V, is dynamic. And in steady state, they're both, if the input C is constant, then S will eventually go to equilibrium. And once S is at equilibrium, V will go to equilibrium. And then you can represent the whole system as V equals sigma of S. So that's kind of the way we've been treating artificial neural networks all along. It's really this dynamic process, but if you let the dynamic process sort of play out, these things reach equilibrium. And then you basically can just think of the neuron activity, V, as a nonlinear function of the input current, S. Okay, but we're not going to make it that simple because we like dynamics. Dynamics are cool. So let's talk about recurrent networks. The feedback afforded by recurrent connections can lead to interesting dynamics. So consider a neural integrator. Well, so what's an integrator? An integrator is when you have some input value. Let me just draw some input here. It's going to be 0 for the first second, then it's going to be 1, then it's going to be 0 for a while, then minus 0.5, and then 0 again. That's the input. If we want this to be an integrator, I know it says decoded value, but the idea is to decode from a population the integral. Anyway, probably that's not a very good label. Let's think about what the integral of that signal, of that input is. So for the first second when it's 0, the integral of 0 is 0. For the second second though, this thing has a value of 1, and so we're basically going to be computing the area of that progressively over time. So if for 1 second it has a value of 1, the area under that little square is 1. So after that second, it builds up to a value of 1. Because this is the integral of that thing dt. And you can also go the other way. You can think of, so the slope of this thing is 1. And this thing's basically giving us the slope. So that going this way, d by dt. Okay, then it's for the next second, the input is 0, so we don't integrate anything. For the next second, after that, the input is minus 0.5. So this thing's going to go down in value, but after that 1 second, it's only gone down 0.5 in total. Then for the next second, the input's 0 again. So you can see this plot on the bottom is the integral of the plot on top, or if you like, the plot on top is the derivative of the plot down below. So you can implement an integrator using a recurrent neural network. So let's do that. So consider a fully connected population of n neurons. So we have input x coming in here. Now I'm showing the encoders and decoders explicitly as its own little box. And then they basically compute, that little box computes the input current. So we can think of this as the encoding. And that input current goes into this population. Now this population has a value, which I'll call y, and an activity, which I'll call v. So y is the value that's being encoded, the sort of vector type notion of the vector being encoded. Think back to the population coding video lecture. We had two different representations of the same data. We had this vector of numbers, and then we had a whole bunch of neuron activities. And when you take this vector of numbers and feed it into the population, you do the encoding, that vector of numbers gets encoded or represented by the collective activities of those neurons. So y is the value being encoded, and v is the set of neuron activities that encode that data. Okay. Now, we could encode from that y and even call it into some variable z, whatever. It get passed down to some other population, whatever. But we can also take this and feed it back into itself. We can re-encode it. So we've got these decodings, this one here and this one here, and we can re-encode that back into the population. Just multiply it by the encoding weights and add the biases, and back in it goes. So here we have the recurrent connections. Or you could write as W is the decoding weights times the encoding weights. Now for the identity decoding D, we get V times D is approximately equal to Y. That means if you look at the vector of activities in the population, multiply by the decoding weights, then you get the vector that was encoded, right? That's a way of going from the activity space to the data space. So we're just decoding what was encoded, and we can re-encode that on the other side. So this, I'm claiming, is a neural integrator. So it's taking some input x, and it's encoding that, but in addition to that, it's recycling its internal state and re-encoding it. And so if there's no input, when x is 0, then our goal is to simply, we simply want our population to maintain its value by re-injecting the current. Because if you don't re-inject it, if you don't do this loop thing here, then as soon as you turn the input off, this population is going to encode 0, and that's not very interesting. So for it to be an integrator, we have to have this recycled thing, this recurrent connection, re-injecting its current value into the population. So that even when the input goes to 0, the population still keeps re-encoding its own value. Okay. So that's what that connection does, that recurrent connection does. So that's great, but that's not integrating yet. What about the input? How does the input get incorporated into this dynamics of this recurrent network in a way that it does the integration? So for this, we let the time dynamics be dictated by the synaptic time constant. So we're going to let tau sub m equals 0. Essentially, the V updates super quickly. It's basically always at equilibrium. So basically, V equals sigma of S all the time. Whatever S is doing, V is right there. So there's no dynamics per se for V. So this V, by the way, is the same, like those are neural activities. So they're basically the same V's that I'm talking about up here in these differential equations. Because the neural activities. Okay, so V is constantly at equilibrium. Whatever S is, V just immediately computes sigma of S. But the S is dynamic, so we still have this differential equation. Now, instead of writing plus C, I'm going to write there is plus C, which I'll write over here. But in addition to that, that's basically input like from X. We'll deal with that in a second. But there's also this recurrent input. So sigma of S, this is V, times W, the connection weight matrix, the decoders times the encoders, plus the bias. So this is the recurrent current, I guess. So that part we've established. Now what about the input going from X into C? So to get the input current C, we need to encode the input value X. Quick joke. I want to die peacefully in my sleep like my grandfather did. Not screaming in terror like the other passengers in his car. Okay, so to encode X, what happens? Well, X needs to be multiplied by the encoding weights. That will be the input. That's basically the part we're trying to add. So this differential equation up here, let me write a slightly different form of it, because this one has the tau s on the left-hand side, but an integrator doesn't. An integrator just looks like this. ds by dt equals c, whatever the input is. Whatever c is, s is going to integrate it. Notice there's no time constant there. Okay, so we're going to move the time constant to the other side. So ds by dt is equal to, this thing here is v times w plus beta minus s over tau s plus c tilde. So this c tilde is just the old c divided by tau sub s. So let me write that in. No, sorry. This c here is not the old c divided by tau sub. I mean, it's related to this c by a factor of tau sub s, but what we want is this thing to be xe, because as I said, ds by dt equals that thing. That's what the integrator does. So now if we move tau s to the other side again, tau s equals times ds dt equals vw plus beta minus s plus tau s times xe. So suddenly now this input is being multiplied by the time constant, and we want that because it's basically brings that input into the proper scale so that the integrator is going to build up its state at the right rate. Okay, so now manipulating this equation a bit, this W is actually the decoders times the encoders. So I can factor out the decoders. Now I've got an encoder here, so I'm going to put those things in the brackets like that. I just factor the E and the encoders out. Then we have to plus the biases minus S. So what are these pieces? This V times D here, that's basically just the internal state that's being re-injected. So I can write that as Y. And this part here, tau S X, that's the input scaled by the synaptic time constant. So re-injected state. And this is the input scaled by synaptic time constant tau sub S. So this tells us that we have to take our input and multiply it by the synaptic time constant. So looking back at this diagram that we had of our population, we have D, the identity decoders, that's a weird Y, and we have to multiply our input by tau sub S as it comes in. Scale by tau S. So if you do that, you'll get this sort of behavior. So, I mean, I've already kind of described this behavior. This was just a Python demonstration I used to show. I think I have a better demonstration now. But for what it's worth, this is the output Y of t. This input is X of t. X of t. And you can sort of get a sense for it. Here we're at 0.25. Why? Because we were integrating 0.5 for half second. I guess I can write this up here. Okay, so that blue line is, in fact, integrating that red dotted line. So because of this thing, because of this analysis, the re-injected current can include other factors. So this part here, this re-injection, has to be there. You have to re-inject Y, but you can also re-inject other things. You can use other functions of Y. In fact, instead of having X coming in, the X could actually be a re-injection of the current state. So now you can include not just integrating input, but you can have sort of dynamical systems that continuously integrate or depend on the current state. Well, that's probably better if I just show this differential equation. The state of Y depends on, I guess the rate of change of Y depends on some function of Y. That's a differential equation. So F could be some sine function. It could be, if it's just Y, then it's just an integrator. If it's, if it's Y, it's not an integrator. If F of Y is a constant, then it's an integrator. If F of Y is equal to Y or something, it's going to be exponential growth, exponential decay if it's minus Y, these sorts of things. So these are lots of different dynamical systems that you can implement by just changing F. So again, looking at this little diagram of our recurrent population here. So we have our identity reinjection here, which is part of what the population has to do. But in addition, you can have this other part here. So we can set the input to be f of y. So I'm not reading here. You can get the recurrent network to solve or simulate that dynamical system by setting the input to be f of y. That's what I meant to do. So here we are re-injecting f of y. We just multiply by tau s, because that recurrent connection is not the identity re-injection. This is the part that we actually want to integrate as part of the dynamics. And so that differential equation, that little neural network, recurrent population, will implement dy by dt equals f of y. So let me show you an example of this. A simple harmonic oscillator is dictated by these differential equations here on the left. So it's a two-state system. You have an x and a y, and they're related. Well, there's the differential equation. X depends on y, y depends on x. But if you look at the equations, for any state x, your rate of change, or your sort of velocity vector, is going to be perpendicular to where you are. So this little vector here is negative theta y, theta x. Is that correct? I guess maybe it goes the other way. No, that's right. And so if no matter where you are, your velocity is perpendicular to you, you're going to follow a circular trajectory. So the solution of this, whoops, I just erased everything. The solution is basically traveling in a circle. That's a simple harmonic oscillator. That's the solution of those differential equations. Now, as a network, a recurrently connected network, we have this internal state xy, and we need to re-inject it with xy, with the identity. That basically makes it, think of it as like Euler's method. With Euler's method, you replace the current state with the current state plus some increment, right? So this is the current state for Euler's method, if you like, and then we add to it an increment. Let me have it coming in from over here. So this is the thing that's multiplied by tau s, and it has the form, the decoding, negative theta y, theta x. So theta, by the way, is the you can think of it as the velocity, or the speed, but it dictates how quickly you oscillate. If theta is small, you go around slowly. If theta is big, you go around quickly. So here's this recurrent dynamical system. We have the identity reinjection, and we have the we feed back this dynamical system here. So let me show you that in Nengo. So here I'm starting out with just a normal Nengo population. You've seen this before already. Let me now change this population A into be two-dimensional, and I'll make it a couple hundred neurons. Can I make this bigger? There we go. Okay, now we're going to need two inputs, 0, 0. Okay, now I need to re-inject the state, so okay, Nengo connection from A to A, and the transform is going to be 1.02. So what it's going to do is re-inject it with a little bit of a multiplication. So if you set it equal to what this transform does is basically a linear multiplier. It's kind of like the tau sub s, but it's not related to tau sub s. It's This is just to make sure. So these simple harmonic oscillators, ideally they maintain the same radius, but in reality, if there's noise, the radius can reduce or grow. If the radius is going to grow too much, okay, I should add something here. So I'm setting the radius equal to 1. So the decoding, when Nengo computes the decoding weights for this ensemble, it's going to sample things in the radius of 1. So this ensemble will be good at decoding things between -1 and 1. Outside of that, and that's a magnitude of -1 and 1. So it's a 2 vector. So any vector that it's encoding that's of size up to from 0 to 1, it can encode effectively. Outside, or vectors bigger than a magnitude of 1, it's not trained on those, so it's not going to be good at it. So this kind of acts like a saturation point. This transform, the reinjected state is going to grow it by 2%, but at the same time, those neurons, this ensemble is not good at representing vectors longer than a length of 1. So it's going to grow it towards 1, but then it's going to stay at 1. So that's a good way. It's kind of a good way of taking advantage of the saturating properties of these neurons to keep to stabilize this simple harmonic oscillator. Okay, so I also need to add another connection. This is the one that injects the thing with the thetas. So I'm going to define a simple harmonic oscillator, and it takes input the state. So this function I'm going to use to make for my other connection. I'm not done that function yet. I'm just going to show you how I'm going to use it. Nengo connection from A to A, function equals simple harmonic oscillator. Whoops, oscillator. Okay, so this function is going to take the two-dimensional state of a two-dimensional thing that's encoded in the population and create a two-dimensional vector that it feeds back into it. And so let me create a synaptic time constant 0.04, 40 milliseconds. So this connection has to have that time constant. Do I need that anywhere else? No, okay. Okay. Now theta, I'm going to set it equal to 2. So dx0 dt, this is the first differential equation. It's negative theta times y. So we need to say negative. Why do I have positive? I'm looking at my solutions here. Okay, whatever. Tau s times theta times, and then it multiply by 2 pi. dx1 dt is tau s times theta times 2 times pi. So I return dx0 dt, dx1 dt. So it's just evaluating that right-hand side of that system of differential equations. Okay, so this little feedback loop actually stands for both of these connections here. So let's see, when I run it, so it's better to look at the xy value. Okay, that's not working. What have I done wrong? oh, I didn't multiply by the x itself, times x1, that's the y value, times x0. So interestingly, it went up, basically the thing grew to as big as it could grow, and then it stopped there, because I wasn't multiplying by the state itself. Okay, there, woo. Let's slow things down a little bit. So you can see it's going around the circle. The radius is a bit bigger than 1, but it's doing it. And what's the period of it? If I stop it, let's set this thing to be 1 second. You may not be able to see it down here. So now we're seeing 1 second. So looking at the blue curve here, in 1 second we go 1, 2, 3, 4, 5 and a bit. That's more than I thought it would be. That should be oscillating at 2 hertz. So maybe I need to also add that. So you have to give it a kick to get away from, there we go, that looks a little more reasonable now. So the reinjected current is also multiplied by tau s. Oh no, right. The synapse has a particular time constant. This is not multiplying that input by tau s. This is just saying that that synapse has that time constant. This synapse has the same time constant, but the reinjected current is just multiplied by something slightly bigger than 1. The connection that's implementing the simple harmonic oscillator, you do have to have tau s in it. Okay, so in this case, if you look at 1 second of time, looking at this green thing, it goes 1, 2 oscillations. So the theta is in fact giving the frequency. So now it should be going at about 1 hertz. And I think you can see that in this 1 second time frame, it does in fact do 1 oscillation. So this is just one example of a dynamical system that you can implement using a recurrent population of neurons. And it opens the door for lots and lots of things that you can do with these networks. I've done things, I've written papers using oscillators to do path integration and represent location, like where you are in space, and they produce similar types of spiking behavior to what you would see in actual grid cells in your brain. And you can produce place cells. That's just one example of the sorts of things you can do with these oscillators, but with these dynamical systems in general. So we've gone through the whole, well, not all of it, a big chunk covering of neural engineering, covering the 3 main things: population coding, transformations using connections, and dynamics using recurrent connections. You can also do learning. You can set up, if you can supply an error signal, you can learn a set of connection weights using a very simple rule. The thing that's interesting about that rule is, as long as you have the error signal, the update for the connection weights is a local phenomenon. You don't need to know some faraway error. As long as you can have the error delivered to you, you can update the weights to reduce that error.